finally, or the next theorem that we're going to look at says this: every graph must have an even number of vertices of odd degree. Now, why is that true? Well, it's true because remember our previous theorem says that if I sum up all the degrees, it's got to be twice the number of edges. Well, if it's twice the number of edges, then that means that if I sum up all the degrees, that number has to be even. But if I don't have an even number of vertices of odd degree, then the number would turn out to be odd. And I know that's not true. All right, so let's look at a couple of examples here. The point is, any graph at all has to have an even number of vertices of odd degree. So let's look at this graph. By the way, every vertex is of degree 2, therefore no vertex is of odd degree. In other words, it's got 0 vertices of odd degree. Remember, 0 is an even number. Now if I look at this graph, I have 2 vertices of odd degree. They occur right here and right here. They're both of degree 3, and that's fine, right? Every graph has an even number of vertices of odd degree. And if I look at this graph over here, again, I claim I have 2 vertices of odd degree, that one and that one. The other vertices are of even degree. So there you go. The theorem works there. Of course, I'm going to claim the theorem works everywhere. Now we have a theorem that tells us when a graph is bipartite. Remember, bipartite means I could take a graph, I could break the vertices up into 2 sets such that every edge is incident with a vertex from both sets. Okay, so this theorem tells us how we can recognize a graph that is bipartite. It's bipartite as long as there is no cycle of odd length. So if I look at this graph right here, guess what? Here's a cycle of odd length, right? It's got 3 sides to it. So what do I say? This graph is not bipartite. Now let's look at this graph. Again, I have a cycle of length what? 3. Well, it's got a cycle of odd length. I can tell you then that it's not bipartite. There's no way you can break it up. Finally, I look at this example right there. The only cycle I see is this one right here. And it has length what? 4. So there is no cycle of odd length. Therefore, I tell you this graph is bipartite. And finally, well, I guess I have a few more theorems to go. The next theorem says the number of vertices in Kn can be computed by this little formula right here, n times n minus 1 over 2. And I'm just going to remind you of some of our Kn's. Here's K1. So n is equal to 1. I claim it's got 0 edges. If I go back to my formula, it would be what? 1 times 0 over 2, which lo and behold is 0. When K is 2, I only have 1 edge. And if I use a formula again, 2 times 1 divided by 2 is 1. K3, I have 3 edges. 3 times 3 minus 1 is 2. So 3 times 2 divided by 2 is 6 divided by 2, or 3. And K4 is going to be what? 4 times 3 divided by 2. 12 divided by 2 is 6. The point is Kn always has n times n minus 1 over 2 edges. If I want to know the number of edges in KPQ, what is it? And the answer is it's simply P times Q. So K10, how many edges? 1 times 0. K11, how many edges? 1 times 1. K22, how many edges? 2 times 2. K32, how many edges? 3 times 2. And above, I have the pictures of each one. Finally, I want to talk about planar connected graphs. Remember, planar means I could draw it without edges crossing. Connected means I could walk from any vertex to any other vertex. And Euler, same Euler as before, developed a formula that said the number of faces is always the number of edges, subtract the number of vertices, add 2. Now, what's a face? Well, in a southern Missouri sense, a face is an area a cow cannot get out. So in this case, and you have to draw it as a planar graph. In other words, you have to draw it without edges crossing to figure out how many faces you've got. All right, so let's look here. Here, I only have one face because the cow can walk anywhere he wants to walk. All right, so I have one face. Notice I have 2 edges and 3 vertices, and lo and behold, the number of edges, or faces, which is 1, is the number of edges minus the vertices, right? 2 minus 3, add 1. Okay, here, how many faces do I have? Well, I have, that's a face, this is a face, there's a face right there, and there's a face. So I claim I have, what, 4 faces. And if you count, I have 6 edges and 4 vertices. The formula works. Why? It's going to always work if I have a planar connected graphs. So it's got to be connected, and it's got to be planar. That is, you need to be able to draw it without edges crossing. Finally, my last example is this one. How many faces do I have? Well, see, I just have, this is one face, and I'm able to walk all the way around here and here and here. So that's one face. There's the other face. So how many faces in this graph? 2. If you count how many edges, you're going to see we have 6. And how many vertices? We have 6 as well. And the formula is going to work. 2 is 6, subtract 6, add 2. So those are some of the theorems dealing with graph theory, and that's all I have to say. Bye.